Hello, it's Peter again. Thank you for watching this series on wireless M-Bus. Today we will talk more about battery lifetime when using the wireless M-Bus protocol. So today we will look into what determines the battery lifetime of a meter or a sensor. And how does wireless M-Bus achieve long battery lifetime? And finally we will show some lifetime estimate examples. So the current consumption in a meter is generally given by 5 sources. The first one is the metrology. So this could be the current consumption of a sensor or an ultrasonic circuitry, the pickup system, or like a pulse counter. Then we have the RF transmission. We have the RF reception, if this is a two-way system. We have the sleep current, and we have the battery leakage, or the leakage in a supercapacitor. And do note that in wireless M-Bus, most of the time the radio transceiver is actually in sleep mode. A very important feature of wireless M-Bus is the method used for two-way communication. So instead of the radio listening all the time for new messages, or even polling for new messages, wireless M-Bus use a technique where the radio receiver in the meter is switched on only for a short time just after doing a transmission. So these short reception windows are typically a few milliseconds. Like in S mode, the receiver is open from 3 to 50 milliseconds after a transmission. And in the T mode, even shorter, just from 2 to 3 milliseconds. In the C mode, the listening window is delayed either to 100 milliseconds or 1000 milliseconds, that is 1 second after the transmission. And typically the listening window is only 2 milliseconds long. In the N mode, we listen after 100 milliseconds or 1.1 or 2.1 seconds. This depends on the data rate used. The listening window is then typically 20 milliseconds. So let's look into some examples. So using mode N at 169 MHz. This is the Radiocrafts module RC1701HP M-Bus 4. So let's say that the metrology typically use 4 microamps in average current. In sleep mode, we typically have 2 microamps. During the transmission, because this is a high power transmitter of 27 dBm, the current consumption is as high as 403 milliamps. A typical transmission lasts for 100 milliseconds, and let's say we have one transmission every 6 hours. This will give us an average current of 1.87 microamps. Then we are listening for 20 milliseconds after each transmission. During reception we have 32 milliamps current consumption, and again this happens every 6 hours, and this gives us a very small contribution. In total we are at 7.9 microamps. So if we look at a battery, a typical AA cell of 2.4 ampere hours, with this average current of 4.9 microamps, we have more than 300,000 hours of battery lifetime. That is more than 35 years. Of course, the self-discharge of the battery and any leakage in the supercap will reduce that number. But it is feasible to build systems with more than 15 or even 20 years of battery lifetime. Another example is looking at mode T operating at 868 MHz using the RC1180 MBUS 3 module. Again, we use the same number for the metrology, 4 microamps. The sleep current is typically 1 microamp. Transmission is using much less power now because we are limited due to the radio regulations. So the transmit current is 37 milliamps, and a typical transmission using mode T is 10 milliseconds. And let's say we are doing a transmission every 1 minute. This gives us a contribution of 6.17 microamps. Again, after every transmission, we listen for a short time, 3 milliseconds. During reception, we have a current consumption of 24 milliamps, giving us an average of 1.2. And in total, we are at 12 microamps. Using the same battery, in this case, we will get 22 years of battery lifetime. So again, we see that it's possible to make a metering system with quite frequent transmissions, but still very long battery lifetimes. So thank you for watching, and see you soon.